Hello everyone, welcome to Civil Galaxy. Myself Dr. Pruthviraj B S. In today's session, we shall see how to analyze a portal frame with the help of Kanis method. So for that, I have considered a simple frame over here. And if we observe here, the length of the column AB is given as 3 meters. And the length of the column here CD is also given as 3 meters. And the moment of inertia for both are given as I. So if we exactly cut this frame at the center, we are going to get an identical mirror image. So based on this one, to be very specific, we can call this particular frame as a symmetrical frame. So whenever we are having a symmetrical frame, we need not consider the lateral sway or the sway component into the consideration whenever we are analyzing the symmetrical frame. So from our previous classes, we have learned how to analyze a beam with the help of Kanis method. So similarly, the procedure for analyzing the frame also remains same, where the first step here will be to calculate the fixed end moments. So first step will be to calculate the fixed end moments. So here if you observe, for span AB and CD, there is no external loading. So the fixed end moment from A to B and fixed end moment from B to A, also the fixed end moment from C to D and fixed end moment from D to C will be equal to 0, since there is no loading over this span here. Next, if you want to find out the fixed end moment for span BC, which is carrying a UDL of intensity 40 kilonewton per meter over a span of 6 meters. So coming from left to right, we know the formula whenever we are having a uniformly distributed load over the entire span. It is W L square upon 12. Since we are coming from left to right here, it is negative. So if we consider the value here, W they have given, which is minus 40. The total span over here is 6 meters. So 6 square upon 12, which is equal to minus 120 kilonewton meters. Similarly, the fixed end moment for span C to B, the formula remains same, only we are coming from right to left, so the sign changes here, which is WL square upon 12. So this will be equal to plus 40 into 6 square upon 12, which will be equal to plus 120 kilonewton meters. So after calculating the fixed end moments, the next step will be the calculation of, or to find out the stiffness, which is represented by K, and a rotation factor, which is represented by U. So we need to find out the rotation factor and the stiffness. So if we observe in this frame over here, we are having two joints, that is B and C. So I need to consider a table over here to find out the stiffness and the rotation factor. First we will take joint, and for that particular joint we will take the members, and for that particular member we need to find out the stiffness, which is represented by K, and the summation of the stiffness for that particular joint are represented by sigma K, and for that particular member we need to find out the rotation factor, which is represented by U is equal to minus half into K upon sigma K. So here we are having two joints, that is B and C. So let us consider two joints B as well as C over here. So B is having two members, that is B is connecting for B to A also and for B to C also. So we are having two members, that is BA as well as BC. Same, if you consider the joint C over here, C is connecting to a member from C to B and C to D. So here we are having two members, C to B and C to D. So whenever we need to find out the stiffness, we know that we need to consider the far end conditions. If we take the member BA here, B is the near end and A is the far end over here. Since the far end is fixed over here, the stiffness will be equal to I upon L. So here the moment of inertia they have given, which is I upon the total length for member BA here is 3. So this gives a value of, which is 0.33I. So now for member BC over here, see here, this is B, this is C, this is the near end and this is the far end. Since the far end is an intermediate support here in structural analysis, the intermediate support also is considered as an fixed support. So the stiffness, if the far end is fixed, we are getting I upon L. So the value of I they have provided over here, which is 3I upon the total span here is given, which is 6 meters. So this value will be equal to 0.5I. For member CB, if you need to find out the stiffness, C is the near end and B is the far end, and since B is the intermediate support, the intermediate support here is considered as a fixed support. So for fixed support, the stiffness is equal to I upon L. The value of I they have given, which is 3I, and the span here is 6. So this will be equal to 0.5I. And for member CD, if we consider, C is the near end and D is the far end. Since the far end, which is about the point D here, is fixed, so for fixed end, the stiffness is given by I upon L. So here I they have provided, which is I itself here, and the total length here is 3 meters, which will be equal to 0.33I. So now if we take the summation of these two members for the joint B, so this will be equal to 0.83I. Here it is equal to 0.83I. So now we have got the values of K and sigma K. So applying this value over here to find out the rotation factor for particular member, whatever we have considered. So this rotation factor for member BA, here we are getting a value of minus 0.2. For BC, we are having a value of minus 0.3. And for CB, we are having a value of minus 0.3. And for member CD, it is minus 0.2. Next step will be to calculate the rotation contributions. So for that, I have considered a table over here where the intermediate supports, that is B and C, are replaced with the help of two boxes, which is also called as Kanis boxes, because the rotation contribution is only calculated for the intermediate supports and not for the end supports. So what we have to represent in this Kanis table here is, we have to represent the fixed end moment, whatever we have calculated in the step 2. Also we need to represent the rotation factor, whatever we have calculated in the second step. So if we represent the fixed end moment over here in this table, we know that fixed end moment from A to B we have got is 0. Similarly from B to A it was 0, and from C to D it was 0, and from D to C it was 0. Only we have got the fixed end moment from B to C and C to B, which is minus 120 kilonewton meters. I am writing only the values here and not the units. And from C to B it was plus 120 kilonewton meters. So inside this box over here, we have to write or represent the summation of the fixed end moment over this particular joint over here. So if we take the summation, it is minus 120 and plus 0. This will be equal to minus 120 over here, and here for this joint C it is plus 120 and plus 0 it is plus 120 kilonewton meters. So we have to represent the rotation factor also, which we have calculated. In the second step we have got the rotation factor from B to A here. From B to A we have got is minus 0.2, and from B to C we have got the rotation factor as minus 0.3. So from C to B we have got a rotation factor of minus 0.3, and from C to D it was minus 0.2. So now if we just observe over here, we need to calculate the rotation contributions, which is represented here by m dash AB small m dash, rotation contribution represented by small m dash. So m dash AB, and here we will take it as m dash BA. Here from B to C it will be m dash BC. Here it will be m dash CB. Here it is m dash CD, and here it is m dash DC. So since, as we have told, the rotation contribution is calculated only for the intermediate supports and not for the end supports, the rotation contribution about the end support is m dash AB and m dash DC will be equal to 0. So if we need to calculate the rotation contributions, we know the formula, which is given by m dash is equal to U into summation of fixed end moment plus summation of far end rotation contributions. So this is the formula we have to use. So now if we calculate the rotation contribution for this particular here, let us call it as cycle 1 for the iteration process. So for cycle 1, if we consider, which is m dash BA, m dash BA, which will be equal to, there is a formula over here, U into summation of fixed end moment plus summation of far end rotation contributions. So U we have got here, which is minus 0.2 into summation of fixed end moment we have already considered here, which is minus 120 plus, see here now, the summation of far end rotation contribution. So for this particular m dash BA, we are considering for joint B here, this is the far end rotation contribution we need to consider, that is m dash AB. Similarly, the far end rotation contribution here will be m dash CB. So for C, the far end rotation contribution will be m dash BC, and over here it will be m dash DC. So these two far end rotation contributions we need to consider. So here now if we consider for this m dash BA, the far end rotation contribution is m dash AB, the value is 0 since it is a end support, and here it is m dash CB, the value we don't know for the first cycle, so let us consider it as also 0. So we are getting a value of plus 24 kilonewton meter. So this is the value. So this value we need to consider over here, that is plus 24. Now m dash BC, this one, we need to find out the rotation contribution. So here we need to consider the value of rotation factor, which is given by minus 0.3. Rest everything remains same, that is the summation of fixed end moment is minus 120 plus far end rotation contribution here is 0, and the far end rotation contribution is m dash CB we don't know for the first cycle, we will consider it as 0. So the value is plus 36 kilonewton meter. So this value we need to write over here, that is plus 36. Now m dash CB, see here m dash CB, if we consider, the value of rotation factor here is minus 0.3, and the summation of fixed end moment here is plus 120 plus the far end rotation contributions here it is 0 for m dash dc plus the far end rotation contribution is m dash bc over here. We have got a value, new iteration value. We have to consider that one, which is plus 36. So now we are getting a value of minus 46.8 kilonewton meter. So this is the value over here. So this value we need to write over here, minus 46.8 kilonewton meters. So next is m dash c to d. So this value we need to consider over here. We need to find out. So it is minus 0.2 because the rotation factor here is minus 0.2. Rest the value remains same. That is summation of fixed end moment plus 0 about m dash dc plus the new iteration value which we have got for the far end is plus 36. We are having a value of minus 31.2 kilonewton meters. So this value will represent here, which is minus 31.2. So similarly, now we need to go on calculating the rotation contributions. That is, we need to go on to calculate the iteration process until and unless we are getting the same and equal values over here. See here, everything remains same, only here the value keeps on changing. So we shall just consider the we shall consider the fixed end moment as it is, summation of fixed end moment as it is. Only the far end rotation contributions keeps on changing. So here the far end rotation contribution here is plus 0 and the far end rotation contribution, now we have got a new iteration value which is minus 46.8, which fetches a value of plus 33.6 kilonewton meters. So next here it will be plus 0 minus 46.8, which gives a value of 50.04 kilonewton meters. So this value will write over here, that is plus 33.6 and this value which is plus 50.04. So next, if we consider for m dash cb and m dash cd, which is 0 because here m dash dc, first one is 0, and here we have got a new iteration value which is plus 50.04. So here also it is repeated the same. So we are getting a value of minus 51.01 kilonewton meters and minus 34.01 kilonewton meters. So this value over here we have to write here, which is minus 51.01 and this value over here minus 34.01. So we can see here how the values are changing. So we need to consider the iteration process until we get the similar values. So probably this was the second cycle. Now we'll go for the third cycle over here. This is cycle 3 now. See here. So the far end rotation contribution here remains same. Now we are getting a new iteration value over the far end rotation contribution. We'll consider that one, which is minus 51.01. Here also minus 51.01, which gives a value of 34 plus 34.20, and this gives a value of plus 51.30 kilonewton meters. Here also it is kilonewton meters. So this value we need to consider over here, that is plus 34.20, and this value which is plus 51.30. So here also it is 0 plus 0 because the far end rotation contributions about m dash dc is 0, and about here, that is the new iteration value which we have got is plus 51.30. Here it is plus 51.30, which gives a value of minus 51.29 kilonewton meters, and here we are having a value of minus 34.26 kilonewton meter. So this value will write over here, which is minus 51.29. Here it is minus 34.26. So if you observe over here, the value are not similar over here, so we need to go for the fourth cycle. So everything remains the same, only the far end rotation contributions keeps on changing. See here, so this remains 0, and here we are getting a new iteration value, that is minus 51.29, which comes to a value of 34.28 kilonewton meters. So here it is plus 34.28. So here it will be 0, and here minus 51.29, which gives a value of plus 51.42 kilonewton meter. So here it is plus 51.42, and here it is 0. Here it is a new iteration value which is plus 51.42. Here 0 plus 51.42. So we are getting a value of minus 51.63 kilonewton meters. It's for this one here, minus 51.63, and here we are having a value of minus 34.28. So minus 34.28 kilonewton meters. So minus 34.28. So now if you observe, the values are almost similar. So probably in the fifth cycle we are going to get the same values. So here just changing the far end rotation contributions. See here. So here we are having a new iteration value for the far end rotation contribution, that is minus 51.63, which gives a value of plus 34.28 kilonewton meters. So here it is plus 34.28. Here it is minus 51.63, which gives a value of plus 51.42 kilonewton meters. So here it is plus 51.42, and here the new iteration value is plus 51.42. So plus 51.42, which gives a value of minus 51.63 kilonewton meters and minus 34.28 kilonewton meters. So this value will put over here, minus 51.63 minus 34.28. So now if we observe, we are having the similar values. So this value, say this value, we can consider it as the final rotation contributions while we are calculating the final end moments. So this value we need to consider the final for the calculation of final end moments. So now going for the last step before calculating the support reactions and maximum bending moment. See here. So this is step 4. So for step 4, if we need to calculate the final end moments, which is final end moments. So we know to calculate the final end moments about A to B, the formula fixed end moment from A to B plus 2 times rotation contribution about the near end plus 1 times rotation contribution about the far end. So the fixed end moment about point A to B we have written here, which is 0, and here 2 times rotation contribution about the near end. About the near end, the rotation contribution here is 0, plus the far end rotation contribution, 1 time far end rotation contribution. M dash BA, we have considered the final value here is plus 34.28. So the final end moment from A to B is 34.28 kilonewton meters. So similarly, applying the formula for other members also, that is from B to A, we are having a value of, from B to A we are having a value of 68.68 kilonewton meters, and final end moment from B to C we are having a value of minus 68.68 kilonewton meters, and final end moment from C to B is plus 68.68 kilonewton meters, and the final end moment from C to D, here we have got minus 68.68 kilonewton meters, and fixed end moment from D to C we have got minus 34.28 kilonewton meters. See, observe the values over here. Moment about A to B is plus 34.28. Moment about DC is minus 34.28. Since in the beginning we have discussed that if we cut the frame exactly over the half, we are getting an identical mirror image. Also about the support B over here, we are having equal and opposite moment. If you see here, from B to A it is 68.68, and from B to C it is minus 68.68. Same for C to B, it is 68.68, and from C to D it is minus 68.68. So based on these values, we can further calculate our support reactions and maximum bending moment. So here representing this one here, which is rotating in the clockwise direction because it is positive, we will consider here, which is 34.28 kilonewton meters, and from B to A also it is positive. Let us take here, it is 68.68, and from B to C it is negative. So here it is negative, which is 68.68, and from C to B it is positive over here, which is 68.68, and from C to D it is negative over here in the anti-clockwise direction, which is 68.68, and D to C also here it is negative, we can in the anti-clockwise direction, which is 34.28. So now based on these values, we can further calculate our support reactions. So see here. See here. So the last step here, which is step 5, to calculate to calculate support reactions and the maximum bending moment. So here if we consider first span, so let us consider a span AB over here. I will write the span over here as it is. So this is A and this is B over here. So let us consider a reaction about here, calling it as RAB, and here this one as RBA. So here we are having a value which is in the anti-clockwise direction, that is 34.28, and here a clockwise rotation which is 68.68 kilonewton meters. So now if you want to find out the support reactions, first we shall take the summation of any one point to be equal to 0. In this case I will consider about A is equal to 0. So if the moment about here is 0, this RAB, force multiplied by perpendicular distance, since the force is moving over the same point and the distance is 0, this will be equal to 0 over here. So RBA, here it is 3 meters from A to B, which they have given the value over here. Since it is rotating in the anti-clockwise direction, which is minus RBA force multiplied by perpendicular distance over here is 3 meters. So minus RBA into 3, and we are having one clockwise moment here which is plus 34.28, and here one anti-clockwise moment that is minus 68.68 to be equal to 0 over here. So now we are having a value of RBA which is equal to 11.42 kilonewton meters. So now RBA value which is coming in the negative x axis, we will call it as here, which is going in the left direction of the x axis. So 11.42 kilonewton meter. So here if we take RAB plus RBA and here it is plus RAB minus RAB, since it is in the negative x axis, to be equal to 0. So here also RAB also will be equal to 11.42 kilonewton, which is in the right side direction. Sorry, here it is not kilonewton meter, it is only kilonewton, since it is a reaction. 11.42 kilonewton, and here it is 11.42 kilonewton. So now if you want to calculate similarly for span BC, see here, for span BC over here, this is B and this is C. Let us call it as RCB here and RBC, carrying an intensity of UDL which is 40 kilonewton per meters at a distance in the span of the member BC here is 6 meters, and here I am having an anti-clockwise movement that is 68.68 kilonewton meter, and here it is positive 68.68 kilonewton meters. So now if we just consider any one point, that is sigma, moment about B is equal to 0 about this point. See here, so force multiplied by perpendicular distance rotating in the anti-clockwise direction, it is negative. So minus RCB into the total length, that is 6, and also we are having a UDL which is rotating in the clockwise direction, that is plus load multiplied by perpendicular distance into half the distance, the CG for UDL, and here we are having one anti-clockwise negative moment minus 68.68, and here one positive which is plus 68.68 equal to 0. So now if we calculate the we calculate the value of RCB, we are getting a value of 120 kilo Newton. So now if I take sigma Fy is equal to 0, which is RBC plus RCB minus here 40 into 6 is equal to 0. So the value of RBC also will be equal to 120 kilo Newton. So this is the value which we have got. So now we know that since it is carrying an UDL, the maximum bending moment exactly will be at the center at a distance of 3 meters. So this point, if we consider it as point E, we can calculate the maximum bending moment at point E, and we can represent it by ME. About this point over here, if you consider from the left direction, here it is RBC into this distance 3 rotating clockwise, so positive. So here it is RBC into 3 minus the load over here, which is minus 40 into 3 into 3 by 2, and here you are having one anti-clockwise moment which is minus 68.68. So the maximum bending moment about E, we are getting a value of 111.44 kilonewton meters. Similarly, if we want to find out for span CB over here, see everything is similar over here for span AB. Same values will be applied over here for span CD. Since it is a symmetrical beam, it is identical. Only thing is that if we just take for span CD over here, the span, that is the reaction from D to C, will be in the negative X axis, and for R, reaction from C to D will be in the positive X direction. So here RCD value will be equal to 11.42, and similarly RDC value will be equal to 11.42 kilo newtons. So based on these values, whatever we have got, we can draw the shear force diagram and the bending moment diagram. But only one thing we have to remember is that whenever we are plotting the shear force and bending moment diagram, we have to consider the each member separately to represent the shear force diagram and bending moment diagrams. So similarly, we shall see few more problems related to frames by using Kanis method in the coming classes. Thank you.